This is the seventh talk about basic electronics. The purpose of this talk is to explain a few concepts about amplifiers relevant to the neurophysiology board examination. This talk will have two sections. The first section will be conducted in a conversational format. It will be brief. It will provide a general overview of amplifiers. The second section will be conducted in a question and answer format. It will provide a more detailed explanation of amplifiers. I will start by showing you a model of an old EEG machine. The arrow points to two triangles. A triangle with a line from the apex and 1, 2, or 3 lines at the base is the most used symbol for amplifiers. The line from the apex represents the output of the amplifier. The line or lines at the base represent the input of the amplifier. In this model of a modern EEG machine, you can see also two amplifiers represented by brown triangles. So amplifiers were needed in the past and are still needed presently to record brain electrical activity. Amplifiers are of two types: single-ended, which only have two inputs, one of them referenced to ground, and differential amplifiers. Differential amplifiers have three inputs, one of them for the ground. I will talk about single-ended amplifiers first. Single-ended amplifiers have two functions: amplification and polarity control. I will first address amplification. In this frame, I have represented a single-ended amplifier. I will spend a few minutes describing this important element of an EEG machine before talking about amplification. I have labeled the input as E1 and E2. The E stands for electrode. V in indicates the voltage going in, and V out the voltage going out. The arrow in this frame points to the voltage going in. We must remember that the voltage at E1 indicates the difference in electromotive force between E1 and E2. We must also remember that since E2 is attached to the ground prior to entering the bulk of the EEG amplifier, its value as far as the bulk of the amplifier is concerned is mathematically zero and electrically neutral. On the other side of the frame, indicated by the arrow, is the voltage going out. In this frame, I have added a dashed line and connected it to the output of the amplifier. This line connecting the ground to the output is usually omitted in most representations of single-ended amplifiers, but it is understood that output voltage is also given in relation to the ground. So now that we have talked about the basic structure of the single-ended amplifiers, I will start talking about amplification. The meaning of amplification is well known to all. Amplification implies augmentation. This frame demonstrates an example of amplification. The arrow points to 10 microvolts. It implies that a 10 microvolt signal is coming into the amplifier. In this new frame, the arrow points to 100 microvolts. It indicates that 100 microvolts are coming out of the amplifier. Amplification is a function of the gain of an amplifier. Gain is a ratio of the output voltage divided by the input voltage. In this case, when the voltage going in is 10 microvolts and the voltage going out is 100 microvolts, the gain of the amplifier is 10. Often, this number is expressed by writing it inside the amplifier, as I have done in this frame. In addition to amplification, the second function of a single-ended amplifier is polarity control. This function consists of inverting or not inverting the polarity of the output signal in relation to the input signal. We call inverters or negative amplifiers those that change the polarity of the signal. Single-ended amplifiers that invert the signal are often labeled by a negative sign inside the triangle. Single-ended inverters amplifiers may, as in this case, transform a positive signal going in the amplifier to a negative signal going out of the amplifier, or a negative signal going into the amplifier to a positive signal going out of the amplifier. On the other hand, non-inverters or positive single-ended amplifiers maintain the polarity of the signal. They are labeled by a positive sign inside the triangle. Whether, as in this case, they get a negative signal coming in and put out a negative signal, or as in this other case where a positive signal is going in and also a positive signal is going out. So far, we have talked about single-ended amplifiers. At this point, I would like to change the focus of our talk from single-ended amplifiers to differential amplifiers. Differential amplifiers are built by using two single-ended amplifiers with their output attached to a second form of amplifier, at times called drivers. This type of amplifiers, in addition to providing amplification, they add discrimination to the function of the differential amplifier. So Differential amplifiers, in addition to amplification and polarity control, they have a third function that is called discrimination. Discrimination is accomplished by rejecting common activity. In EEG lingo, we refer to this function as common mode rejection. Common mode rejection implies rejecting what is equal in a signal and keeping untouched what is not. As you can see in this frame, if two signals are processed by a differential amplifier, the output signal can end up being very different from the input signal. As you can see, the curvy lines going into the amplifier are manipulated by the amplifier so as to produce an output signal consisting of a quick up and down signal only. This quality of a differential amplifier is given as a ratio. Hence, we talk about common mode rejection. A good differential amplifier will have a high common mode rejection ratio. Most of what is common is rejected, and all that is equal will be kept as is, with no distortion or amplification. A 10,000 to 1 common mode rejection rate is acceptable. This is equivalent to 80 dB. Remember, it is easy to convert common mode rejection rate from natural numbers to decibel when the amplitude ratio consists of a 1 followed by zeros. Just count the number of zeros and multiply by 20. I will show you in this case. As you can see, here we have 4 zeros. We take the 4 zeros and multiply them by 20, and obviously this is equal to 80. So we say that such an amplifier has 80 decibels. 80 decibel is a good rejection mode. But the common mode rejection ratio of most commonly used differential amplifiers is probably in the value of 100 decibels. The recommendation from the International Federation of Clinical Neurophysiology is 110 dB. I will now start the question and answer section. The first question is: single-ended amplifiers are connected to a ground. A, true; B, false. Single-ended amplifiers have 2 pins. One pin connected to the area of interest here is labeled E1, and a second pin here labeled as E2 that is used as a reference. This electrode, by virtue of its connection to ground or to a neutral point, represents an electrical neutral area or a mathematical zero. Single-ended amplifiers have an output voltage that is also given in relation to the ground or electrical zero. I have omitted this element in this frame. So the answer to this question is true. Next question. Single-ended amplifiers are depicted by using only one type of symbol. A, true; B, false. Single-ended amplifiers are represented differently in different books. In this frame, I am showing you the representation used in Misuli's book. In this book, single-ended amplifiers are represented as triangles. One input pin is labeled active, the other is connected to a line labeled reference that also extends forward, as you can see in this frame. In addition, from the tip of the triangle is the output. Other representations of single-ended amplifiers include a triangle with a line to indicate input and another line to indicate output, and the symbol for ground attached to the triangle. I like this representation because it highlights that the ground serves as a reference for the input and the output. Yet, probably the most used symbol used to represent a single-ended amplifier is a triangle with a line at the base shaped like the back of an arrow and a line at the front from the apex ending in an arrowhead. So single-ended amplifiers in this frame represented by 4 different symbols, whether written or understood, are always connected to a ground or neutral point at the input and at the output. Remember, voltage cannot exist without a reference point. So the answer to this question is false. In general, the type of ground connected to the ground slot of a single-ended amplifier could be A, earth, B, the chassis of the equipment, C, a galvanic neutral point, D, all of the above. The terminology for ground is confusing. We talk about earth ground, chassis ground, digital or floating ground, and patient ground. They all have a different meaning. The symbol for earth ground is a vertical line with progressively smaller horizontal lines, as you can see in this frame. Earth grounding of an amplifier consists of connecting one of the input pins of the amplifier through a wire to a metal rod that is interred in the earth. This is usually achieved by connecting a wire designated as ground to the water pipe system of a building. Earth grounding serves 2 purposes. The first is as a return path for electricity. I will show this quality of electricity in the following frames. This drawing represents a power plant with a tower and 2 broken wires laying on the ground, the surface of the planet. As pointed by the arrows, one on the left and one on the right. In such situation, a return path for the current will develop between the 2 fallen cables going through the earth. I hope you remember when we spoke about electrical safety, when we said that if a man floating in space touches one of a pair of wires carrying large voltage, he will not get electrocuted. On the other hand, If instead of floating in space, the person is standing on the ground, things do not go the same way. He will get electrocuted. This occurs because the man is now serving as part of the return path for current by connecting the cable with planet Earth. The second purpose of Earth grounding is to provide a neutral galvanic point. A neutral galvanic point implies a place where voltage is zero in relation to everywhere else. Grounding a single-ended or differential amplifier also makes use of the Earth in this context. Think of this phenomenon as the volume of Earth being so large that it can dilute all current connected to it to a value that we have come to call zero. The second type of ground we mentioned was chassis ground. You can see the symbol for chassis ground in this frame. The best way to think about chassis ground is to think of a car battery. The battery in a car has one pole directly connected to the chassis of the car, while the other pole of the battery is connected to different electronic equipments. These equipments themselves are connected to the chassis of the car. This arrangement offers a return path for electricity. Offering a return path for current is the only function of a chassis ground in a car, since the connection to Earth is neglected by the high resistance of the rubber tires, and the volume of the chassis is not big enough to dilute voltage to the same extent that will be diluted by the Earth planet. The third type of grounding is digital or floating ground. The symbol for digital or floating ground is as you see in this frame. The only function of a digital or a floating ground is to provide a galvanic neutral point. A simple way to have a conceptualization of a digital or floating ground starts by thinking of a circuit with two batteries being measured by a voltmeter. In the case presented in this frame, since the batteries are 5 volts each and measured in such a way as to add their value, their combined voltage will be 10 volts. On the other hand, if we invert the contacts of the voltmeter as shown in this frame, and if the voltmeter is capable of displaying negative values, the voltmeter will show a negative 10 volts. Negative 10 volts is a mathematical term, not a galvanic term. Now, if we measure the voltage by placing one probe between the two batteries and the other to the circuit above the second battery, the voltmeter will show a value of 5 volts. If we were to invert the connection of the voltmeter and measure from between the two batteries to the lower segment of the circuit, as shown in this frame, the voltmeter will show minus 5 volts. If then we alter the voltmeter in such a way as to compare the upper and the lower segment previously mentioned, the voltmeter will show a value of 0. This arrangement will thus produce a neutral point. So if we connect the reference leg of a single-ended or differential amplifier to a circuit in the fashion we just mentioned, we will get a zero or a neutral point that can be used as a reference. The fourth type of ground is the patient ground. We call the patient ground to the lead, usually going from the head to the machine that is connected to the pin of an amplifier that itself is in contact with an earth ground or a digital ground. So the answer to this question is D. Please notice that this question states in general at the beginning of the question statement. Next question. The amplifier above should be labeled A. Single-ended inverting amplifier, B. Single-ended negative amplifier, D. Single-ended positive amplifier, D. None of the above. This frame represents a single-ended non-inverting amplifier. These amplifiers respect the polarity of the signal. So if we refer to an up-pointing wave as a negative wave, and we find such a wave at the input of a non-inverting single-ended amplifier, at the amplifier output, the wave will be reproduced also as a negative wave. And if we refer to a wave pointing down as a positive wave, and we find such a wave at the input of a non-inverting or positive single-ended amplifier, at the amplifier output, the wave will be reproduced also as a positive wave. The single-ended non-inverting amplifiers are often labeled by introducing a positive sign inside the triangle, as I have done in this frame. Single-ended inverting amplifiers, on the other hand, invert the polarity of the signal. So, a negative signal appearing at the input of a single inverting ended amplifier will be displayed at the output as a positive signal, whereas one appearing as a positive signal at the input of an inverting single-ended amplifier will be converted to a negative signal at the output. The single-ended inverting amplifiers are often labeled by introducing a negative sign inside the triangle, as I have done in this frame. So the answer to this question is C. Next question. Which of the following elements is the main component of an amplifier? A. Diodes, B. Capacitors, C. Transformer, D. Transistors. This frame shows a transistor. A transistor is an active electrical element. An active electrical element is one that adds voltage to the circuit. The word transistor derives from the words transfer and resistor. Transistors control the transfer of energy across a resistor, and depending on their design can respect or invert the polarity of the electrical activity presented to them. The work of transistors in the past was done by electrical tubes, and in the future are likely to be done by microchips. I will not spend too much time talking about transistors. Suffice to say that transistors are of two types according to the polarity of the middle segment, which is often called the base. Those with a negative charge base are one type, called N transistors, and those with a positive charge base are a second type. They are called P transistors. The base of a transistor is sandwiched between one segment called collector and another segment called the emitter. The symbols for transistors are as introduced in this frame. These symbols derive from the schematic of their structures when connected to a power source. So if we look at this symbol, enlarge it, and then introduce a power source as I have done in this frame, you can see why the symbol for transistor was chosen. So the answer to this question is D. Next question. The magnitude of the power source dictates the limits of an amplification. A true, B false. Using the schematics of a transistor as viewed in this frame, we can explain in a very simplistic fashion their function. Their functions are two functions. I will first address amplification. In this frame, I am representing a brain-generating activity of 50 microvolts entering the transistor and generating an activity of 5 volts. To understand how transistors amplify a signal, I like to think of a water faucet. The water faucet is connected to a water tank. The handle controls the flow of water. Thus, a twist of the handle, which takes little force, makes water to start flowing. And then, if we turn the handle a little more, again using a little force to do so, a great splash of water will come at a great force. So the small voltage used to turn the handle unleashes a big force coming out of the faucet. The analogy between the water faucet and a transistor becomes patent if we think of the minor force used to turn the handle as the voltage going into the transistor. The battery, which has not been presented in these frames as the water tank, and think of the splash as the voltage going out. Another analogy I have found useful is to think of a transistor as the pedal of an accelerator in a car. The force applied to the pedal is minimal, yet the force generated by the car's combustion engine to move the car forward is big. In a way, this is similar as to what happens in a transistor. A few microvolts coming in are turned into lots of microvolts going out. It is important to know that the ability of a transistor to increase voltage is limited by the magnitude of the power source. In this frame, I have represented the maximal amplifying capacity of this transistor as 10 volts. These 10 volts are being unleashed by 100 microvolts. In a transistor with such a specification, an increase in voltage going in, let's say 200 microvolts, will not further increase the output voltage. So the answer to this question is true. Next question. Polarity management is a function of transistors. A true, B false. Transistors, in addition to also confers to the transistor the function of polarity management. This relates to the type of transistor, negative or positive, and to the position of the battery's cathode in relation to the transistor, towards the collector or towards the emitter. So the answer to this question is true. Next question. Differential amplifiers are built by combining inverters and non-inverters single-ended amplifiers. A true, B false. Differential amplifiers are nothing more than a non-inverter single-ended amplifier and an inverter single-ended amplifier combined in a specific arrangement. I will show you this arrangement in the next frame. In this frame, I have represented two single-ended amplifiers as depicted in Misuli's book, with the input to the lower or second pin of both amplifiers going to a ground represented by the unbroken arrow. The single-ended amplifier on the top is a non-inverter single-ended amplifier. The one on the bottom is an inverter single-ended amplifier. In this frame, I have colored the ground inputs to both amplifiers in yellow. And in this new frame, I have brought them to the position between both amplifiers. I have done this to simplify the figure without changing its basic structure. In this new frame, I have changed the geometry of the ground line and introduced the digital ground symbol, but maintain the same functional association. Notice that the ground symbol I am using is the digital ground symbol. I have used the digital ground symbol because in this instance of the two functions of grounding, providing a return path for current and behaving as a neutral point, it is only the later one that is needed. This function can be provided by the digital ground. So the answer to this question is true. Next question. The first step in the process accomplished by differential amplifiers is amplification. A true, B false. If you recall, when we started this talk, we said that there were two types of amplifiers: single-ended and differential amplifiers. We also said that differential amplifiers have three functions: amplification, polarity control, and discrimination. In order to understand how the differential amplifier combines amplification, polarity control, and discrimination, I will, in the next frame, add to this figure of the non-inverter and inverter amplifiers that we are looking at a third amplifier, to which I will refer to as a driver amplifier. The primary function of the driver amplifier is discrimination. In this new frame, I have introduced three waves with the same polarity arising from the brain of an imaginary patient connected to a differential amplifier. I have done so to show you the evolution of brain-generated waves as they are processed by the differential amplifier. Notice that the wave arriving to the upper single-ended amplifier, now forming part of the differential amplifier, is bigger than the other waves. The wave represented in cream color arriving from the brain to the input of the lower pins of each single-ended amplifiers and connected to the ground will be, by virtue of this connection, viewed by the bulk of the amplifier as having no voltage. Thus, the amplifier will consider it for further manipulation as zero voltage or neutral. This will be so regardless of the original amplitude of the wave arriving at the mentioned point. The waves from the electrodes not connected to the ground will arrive to the bulk of the amplifier with minimal distortion. Again, notice that the wave arriving to the upper single-ended amplifier is bigger than the one arriving to the lower single-ended amplifier. The wave arriving to the non-inverter single-ended amplifier will be processed by the amplifier, but obviously the polarity will not be changed. The wave arriving to the inverter single-ended amplifier will be processed by the single-ended amplifier, and the polarity will be changed as expected. In the next step, the differential amplifier will manipulate these values. It will add the values arising from the non-inverter single-ended amplifier to the value produced by the inverter single-ended amplifier. The sum of these numbers will reduce the signal by subtracting all the amplitude that is common to both waves. The process of subtracting all the amplitude that is common to both waves is what we refer to as discrimination. A second function of the driver amplifier, once the primary function, that is discrimination, is achieved, consists of increasing the magnitude of the signal, let's say to a gain of 5, leading to a wave of 5 times the size of the wave produced after the process of discrimination has taken place. So the answer to this question is false. Next question. The schematization of a differential amplifier includes triangles inside a triangle. A true, B false. So this frame represents the basis for the schematization of the differential amplifiers. This model can be simplified by reducing the size of the triangles and enclosing them in another triangle. Such a change leads to this figure. So the answer to this question is true. Next question. Which of the following qualities is required from a good amplifier? A. Amplitude linearity. B. Phase linearity. C. Adequate bandwidth. D. All of the above. A good differential amplifier must have amplitude linearity, adequate bandwidth, phase linearity, and low noise. So the answer to this question is D. Next question. Good amplitude linearity assures that the output signal maintains the same relation to the input signal regardless of the magnitude of the signal presented to the input of the amplifier. A true, B false. This question addresses the issue of amplitude linearity. I will explain amplitude linearity by working with this figure. In the x-axis, you can see the input voltage. This is given in microvolts. In the y-axis, you can see the output voltage. This is given in volts. The happy face is there to indicate a good amplifier. So, if a good amplifier is introduced to an input voltage of 10 microvolt and produces an output of 10 volts, a good amplifier, when at a different time, as indicated in this frame by T2, is confronted with 20 microvolts, it will produce an output of 20 volts, maintaining the same ratio. I have tried to show this in this new frame. Thus, the ratio increase should be maintained regardless of the voltage introduced. A bad differential amplifier in the same situation will increase at a different rate. So at T1, 10 volts will be produced when 10 microvolts are introduced to the amplifier. Whereas at T2, when 20 microvolts are introduced, the bad amplifier will produce 50 volts. So the answer to this question is true. Next question. Adequate bandwidth and adequate phase linearity are the same thing. A true, B false. An adequate bandwidth measured at -3 dB points must be at least 0.1 to 5000 Hz. This requirement is especially important for amplifiers used for evoked potentials. An amplifier with adequate bandwidth is an amplifier that keeps the same ratio of amplification regardless of the frequency the input signal is presented with. So, if an input voltage coming into a good amplifier has a frequency of 10 Hz and an amplitude of 10 microvolts and it produces an output signal of 10 volts, A good amplifier could also produce an output of 10 volts if a 10 microvolt signal is presented with a frequency of 60 Hz. The third requirement of a good differential amplifier is to have phase linearity. In this frame, I am representing the performance of a differential amplifier with good linearity. A differential amplifier with good phase linearity will increase the amplitude of each period in a wave by the same factor. A differential amplifier with bad phase linearity increases the amplitude of the different periods of a wave by different factors, thus distorting the shape of the wave. So the answer to this question is false. Next question. An amplifier contributes to an artifact-free record by having A high input impedance, B, a low noise design, C, an adequate common mode rejection ratio, D, all of the above. The last requirement of a good amplifier is to be a low noise device. Noise can be defined as any unwanted signal, that is, any element that, if expressed in the EEG tracing, is considered an artifact. The way amplifiers can help to eliminate artifacts are by having a high input impedance, by having built-in components that themselves produce little noise. Current specifications are for noise level produced by an amplifier not to exceed 2 microvolts RMS with the input connected to a neutral and with a band pass of 0.1 to 5000 Hz. The International Federation of Clinical Neurophysiology recommends that the noise level produced by an amplifier should not exceed 2 microvolts peak to peak at any frequency between 0.5 to 100 Hz. This is probably the reason that for brain death determination, an EEG electrical activity of up to 2 microvolts is accepted. Other noise-reducing conditions are achieved by having the amplifiers placed far away from other noise-producing components of the EEG machine, or by the amplifiers being shielded from noise produced by surrounding electronics. The last amplifier factor that prevents noise results from an adequate common mode rejection ratio. So the answer to this question is D. Next question. Electrode impedance should be higher than the amplifier input impedance. A, true. B, false. An important factor in achieving an artifact-free record is for the amplifier to have a high built-in input impedance. I have shown you this diagram before when I talked to you about electrode impedance. It simply states that if the impedance of an electrode is X, the input impedance of the amplifier should at least be 100 times X. So the answer to this question is false. Next question. In order to faithfully reproduce a wave, the initial amplifier impedance must at least be dash than the electrode impedance. A, 100 times higher. B, 10 times higher. C, 100 times lower. D, 10 times lower. Most modern EEG machines have differential amplifiers with very high impedance in the millions. To understand the importance of high input impedance, it is imperative for us to remember that in order to have high voltage in the presence of a fixed current in a direct circuit, resistance needs to be high, and that the same occurs when dealing with alternating current. In the presence of a fixed current, the higher the impedance, the higher the voltage. For this reason, modern EEG machines have amplifier input impedance in the 10 mega ohms range. So do not forget, amplifier input impedance should be at least 100 times higher than electrode impedance, but preferably it should be in the 10 million ohm range. So the answer to this question is A. Next question. How much brain signal would you lose if the resistance between two electrodes connected to the head is 10 kilo ohms and the input resistance of the amplifier is 1 mega ohms? A, 1%, B, 10%, C, 0.1%, D, 100%. Using an amplifier with an input impedance of 1 million ohms and two electrodes with a combined resistance of 10,000 ohms, the loss of brain signal is about 1%. So the answer to this question is A. Next question. Most EEG machines have input resistance value in the range of dash A, 0.5 to 1 mega ohms, B, 2 to 10 mega ohms, C, 20 to 30 mega ohms, D, 20 to 50 mega ohms. Most EEG machines have amplifiers input resistance between 2 million and 10 million ohms, thus producing no significant loss of brain signal. A 2006 American Clinical Neurophysiology Society guideline paper recommends for evoked potential to use amplifiers with input resistance of no less than 100 million ohms. So the answer to this question is B. Next question. A common mode rejection ratio between 10,000 to 1 and 100,000 to 1 is good. A, true. B, false. 10,000 to 1 is a good common mode rejection ratio. This ratio allows 0.01% of a signal common to both electrodes to be represented in the EEG tracing. So the answer to this question is A, true. Using a common mode rejection ratio of 10,000 to 1, how much common potential is required to produce a 50 microvolt potential? A, 100,000, B, 1 million, C, 500,000, D, 10,000. Using a common mode rejection ratio of 10,000 to 1, an output signal of 50 microvolts would require a total of 500,000 microvolts common mode signal coming into the differential amplifier. So the answer to this question is C. Next question. Given the values of E1, E2, and G, and the unit below, 1 charge equal to 1 microvolt, what would be the output value of an amplifier with a gain of 5? A, plus 20 microvolts, B, plus 40 microvolt, C, minus 40 microvolt, D, minus 20 microvolts. You can see the charges stated in the square. I am using this cartoon to illustrate the position of 3 electrodes, E1, E2, and ground. In this new frame, I am representing an area of the brain with different charges and electrodes on top of it. The white circles just introduced represent the catch area of the electrodes. Each of these areas has a number of charges. The area on the top has 3 positive charges and 7 negative charges. So the value under the electrode will be 4 negative charges. The value under the electrode in the middle will be 8 negative charges. The value under the electrode on the bottom will be 12 negative charges. I have in this frame represented in a schematic fashion the result of the mathematical operation that we have just performed. So to illustrate the processing that takes place at the differential amplifier, I will start at the ground electrode. This electrode, by virtue of its connection to a digital ground, is represented as neutral, and so it will be viewed by the differential amplifier as it enters into the 2 lower slots of the single-ended amplifiers. Electrode 1 and 2 also enter the differential amplifier, but they do so at each single-ended amplifier through the upper slot. Remember that the lower single-ended amplifier in the differential amplifier is an inverter single-ended amplifier, and that the top single-ended amplifier is a non-inverter single-ended amplifier. Thus, these single-ended amplifiers will do their expected functions. The non-inverter amplifier will respect the value received from the electrode, thus resulting in a value of -4. The inverter single-ended amplifier will invert the value, thus resulting in a +8. At this point, these values are presented to the driver amplifier, and the common mode rejection ratio of the amplifier will further modify these values. In this case, and for the sake of clarity, the common mode rejection ratio in this illustration is 100%, thus implying that in this fictitious differential amplifier, all that is equal will be rejected. This will leave us with a value of positive 4. That since the gain of the amplifier was set to be 5 times, this will lead to an output of positive 20. Since, as you can recall, we gave each charge the value of 1 microvolt, the answer to this question is A, 20 microvolts. Next question. The amplitude of a wave can be determined by multiplying its height by the sensitivity being used. A, true, B, false. Currently, the voltage of a wave can be determined by simply placing the cursor at the location that we desire to measure, and it will be indicated in a rectangular box. In the past, such a determination was done by manually measuring the height of a wave. For example, the height of this wave is 12.6 millimeters. Next, we would have checked the sensitivity being used. The sensitivity being used in this case is 10 microvolts per millimeter. The voltage of the wave would have been determined by multiplying the height by the sensitivity. In this case, since the height is 12.6 and the sensitivity 10 microvolts per millimeter, the voltage would have been given as 126 microvolts. So the answer to this question is A. Thank you. This concludes our session.